one of the big trends in AI recently has been the rise of so-called flash or mini models. Have you seen these?
Oh, yeah.
These are like variants of the flagship systems of companies like Anthropic and OpenAI.
With kind of the intention that they're faster, probably a little bit dumber, cheaper.
Yeah, exactly. And so the idea is that when you're selecting a model, you can choose between either the thinking model, which will spend a lot more tokens thinking about its output before it actually generates that, or you can select one of these flash or mini models, which are dramatically faster and cheaper to run and basically enable you to do real-time applications that would otherwise be too expensive if you use some of these more thinking-based models. So achieving this speed up isn't due to just a single breakthrough necessarily. Like there's been a lot of advancements that have allowed us to increase the speed with which these models do their computations. But one of the key techniques has always been this thing called speculative decoding. But recently there's been this technique called speculative decoding, also known as SSD.
Speculative squared decoding.
Exactly. Which has made a big splash and has been making the rounds in the Twitter sphere.
Yeah, I saw this. So Tree DAO was on this paper, right?
I was about to say, so the team of folks are all from Stanford. The first author on this paper is actually a first-year PhD student at Stanford. So that's a pretty big initial piece of work that he's done in the first couple of months of his PhD. But anyway, so Tree is obviously well known for his work on flash attention as well as state-space models like Mamba. Before we go into this speculative decoding, do you want to first explain, Pierce, what is speculative decoding to begin with? What is even decoding maybe would be a better starting point?
Maybe we build upon this linearly a little bit where we first and we say decoding. What is that? Then we talk about speculative decoding, cover what that is. And then we cover speculative because they all kind of build on one another.
Sure.
So do you want to cover what decoding is as like a general principle?
A language model by itself is a probability distribution. It's basically just like an engine of a car, right? And I think this is actually a pretty good analogy. Because think about it. It's basically like the engine that lets you produce text. But once you have the language model, you have to decide basically how to wire it up to surrounding circuitry to actually be able to start producing text. And the analogy, this would be like putting an engine into a car so it can actually start driving. And so you have to make certain decisions with how do you use this engine? What do you want to do? The simplest approach is to use something known as a greedy approach, which is take this language model, which is just a probability distribution. It just tells you what is the probability of the next word occurring and just pick that most likely next word, right? That's greedy. But you can start doing a bunch of interesting stuff that isn't just that. Like you can, wire it up to a different language model, or you can use something known as Bayesian decoding, or use a different type of statistical analysis to predict what next word you should use. So I think by itself, you have to understand that like a language model doesn't produce text. It literally doesn't. It's just a probability distribution. You can't do anything with it. It's the strategy that you then use to pick, using that probability distribution, what words you want to select, which is the decoding strategy. It's like you decode from it, right? And speculative decoding is the thing that everyone's been using these last 2-3 years just because it's much faster.
It's this kind of clever mathematical property, if you think about it, where you have the big model, which is the main model that you're doing inference with. And then you have some really small model that usually uses the same architecture and is trained on the same data, but it's a lot fast. You kind of want it to be like roughly order 5x or 10x as fast, which usually means making it 5 or 10x as small. And when you're doing the inference, you're taking your existing sentence that you have right now, and let's say that we're trying to predict the next 5 tokens that are within the sequence. So what you normally do is in autoregressive inference, you feed that whole thing in, you get the next token, you then append that to what you had before, so you have one more word, you feed that in again, you get the next word, and then you incrementally build up to 5 additional words. That's kind of just classic greedy decoding. The cool thing with speculative decoding is you use this smaller model to do that same prediction on those 5 tokens, which again happens really quickly because it's a small model that's doing it. And then once you have that full package, you can just do one additional call to the big model, which then evaluates those 5 words at the same time. So best case, if your small model is really well calibrated and is pretty smart, the big model will validate that all of what you just predicted is correct. And you'll get those 5 tokens basically for the cost of 1 call to the big model plus 5 really fast calls to the small one. And worst case, if only one of them is right, or if you have to just do the whole thing over again, you're not really invoking that much of a time penalty. So on net, you can usually end up with like a 2x or a 3x speed up.
Over the greedy approach.
Exactly. Yeah. Over just calling the big one naively every single token. Okay, Rich. Now do you want to cover speculative decoding?
Sure. So speculative decoding is you take speculative decoding, so where you have this smaller model that's producing text and you have a bigger model that verifies it. This is known as the draft and the verifiers you were saying. And here the important intuition is that one of the bottlenecks of normal speculative decoding is that once the small model has produced text and has sent that text over to the verifier, the small model is just like sitting around. It doesn't really have it has no work to do basically, right? It's waiting for the verifier to tell it, hey, either that was good or that was bad, right? Here, the idea is that when you're producing text as the smaller model, sometimes the smaller model can have a very high confidence that the text will be correctly verified, right? So let's imagine that, the draft model is producing some text, something that is very common, like maybe the user has asked, what's the temperature like in the city? And the small model, as it's producing text,
it's obviously cold,
is saying, look, like,
foggy.
It's going to be pretty foggy in San Francisco. And as it's producing that text, it knows itself that, there's a good chance that this is the right continuation of the sequence. So what it can then do is it can send that to the verifier, but after it's produced that text, it can just say, hey, I am 99% confident that the verifier is going to verify this as being a correct continuation. So let me actually already keep decoding more tokens because I'm pretty confident that, my boss here, the verifier, is going to give me the stamp of approval. So let me just keep generating more text.
Mm-hmm.
And so that basically then lets the draft model keep producing more tokens while the verifier is busy verifying the previous tokens. It's this clever little trick to basically parallelize the work of the draft model with the work of the verifier.
Yeah, it's literally like putting up a PR as an engineer, sending it off to your code reviewer. You're not going to stop working on what comes next. You're going to assume it roughly looks good, and you're going to continue on and do something additional, right?
It's pretty obvious in hindsight. It's been surprising that this isn't something we've adopted before.
Does this kind of rely on the assumption that both models can fit on the GPU concurrently? Because I would think immediately the one challenge to this maybe is if you have these two things doing separate matrix multiplications in parallel, like maybe there would be some memory or efficiency bandwidth limitations to actually try to coordinate those two things in parallel. Does that not really end up being the case?
Not necessarily. I mean, you can have two models running on the same chip in parallel.
Totally.
So I don't think that should be too much of a problem. But I think what this does speak to is the fact that orchestration between different models has become more important than the actual model architecture itself.
Yeah, that's a good point.
Like in some sense, whether the draft model is the exact same version of the bigger model, just a smaller version of it, or a completely different type of model, it's kind of independent of this architecture, this method working correctly.